Okay, welcome to the fourth module of the ePathshala program on the course compiler design. Last session on module 3, we discussed about how to define patterns using regular expression and what happens in the lexical phase of the compiler. This session, we will extend our discussion on the lexical phase, where the objectives of this particular module will be to define patterns using deterministic finite automata and non-deterministic finite automata, and respectively convert a non-deterministic finite automata to a deterministic finite automata. So, to start with our discussion, let us see what is an automata. An automata is basically a transition diagram which is a directed graph which depicts the actions that take place when a lexical analyzer is called by the parser to get the next token. I think you can remember and correlate where we will have integrated the first phase and the second phase of the compiler, where basically the parser will ask for a token and the lexical phase will basically parse a token and give it to the parser for successful sentence validation. So, this is where we are trying to define patterns, and this is one example of an NFA for the operator greater than or equal to. Now, as you could see, there is a start state here, and there is going to be a double circle state. The double circle state is typically called as the final state. So, there should be only one start state, but there could be multiple final states. Now, this is an example of a non-deterministic finite automata, where you will say that some strings will belong to this non-deterministic finite automata if the sequence of edges that will go from the start state to the final state, and if you just list down the edges, that is going to be the string of this particular automata. For example, in this case, I have one path from the start state to the final state. This is one final state, this is another final state, and there is a path from 0 to 6 to 7, and there is a path from 0 to 6 to 8, where 0 to 6 to 7 is going to be greater than or equal to, and the other one is going to be greater than followed by something else. Okay. Now, I am going to call this as an accepting state. State 7 is going to be called as an accepting state. Remember, we talked about what is called as an attribute associated with every token. Now, the attribute this has got is, you will have two components. The first one is the lexeme and the second one is going to be the token. Now, the lexeme is going to be the greater than or equal to, and the token is going to be greater than or equal to, and the lexeme correspond to the relational operator. So, similarly here, if I have just any other string, then I will simply return what is called as the rel of greater than. So, only greater than symbol is there. So, I will basically try to use this. So, this representation of defining a pattern, for here we have the relational operator which is greater than or equal to whatever it is, and supposing say you want to go for something else like double equal to, how will this automata change? I could simply change this to a double equal to instead of the greater than. Okay. So, this is one way to convert this operator. Supposing if I have not equal to, then I could convert this edge to not equal to, exclamation mark followed by equal to. So, you can also use the non-deterministic automata to define patterns for explaining on the validating the patterns for a particular token. Okay. So, our first phase, the primary job is to tokenize, and we have done it using non-deterministic finite automata here. So, the next one is another example where we have this for identifier in C. Last class we saw how to define a regular expression for determining identifiers in the C language, which is nothing but letter followed by letter or digit the whole star. This whole star corresponds to clean closure, and this corresponds to an OR operator, and this corresponds to a dot operator. There is an implicit dot here, letter followed by letter or digit the whole star. So, this is the automata representation for this regular expression, where I have letter followed by letter or digit the whole star. So, I can keep on staying here. So, how many paths exist from the start state to the final state? This is one path, 1 to 2, but I can keep on staying in 2 itself for a longer time. So, that is going to be, I can take this is one path. So, the first string is going to be a letter, second could be letter followed by letter or letter followed by a digit or, and we already know what is a letter. Okay. So, these are examples. Continuing on this discussion, we can define a finite automata as one which is a 5 tuple representation consisting of q, sigma, delta, q naught and f, where Q is a finite set of states, sigma is a finite set of input symbols, delta is a transition function which is a mapping from Q cross sigma to Q, and Q naught is an initial start state, and F is going to be the set of final states which is a subset of Q. Now, if you probably could map this to our discuss example here, this is my start state 1, there are 2 states 1 comma 2, input symbols are nothing but letter or digit. So, I have 3 input symbols, but we already know letter corresponds to capital A to small z, including capital Z and small a, etc. So, that 52 characters will correspond to letter, and digit corresponds to 10 characters from 0 to 9. So, that will be your sigma. Transition function is from the state first, if you take letter, it will go to state 2. So, Q cross sigma will take to Q. Similarly, from the state 2 on letter, you will stay in state 2 itself, and from state 2 on reading digit, again you will stay in state 2 itself. So, this is your transition function. Now, this transition function is what we call it as represented by sigma, delta, where you have a Q cross sigma to Q mapping. And you say that every string, this is a particular and important characteristic of a deterministic finite automata, where there is exactly one path for every string from the start to the final state. Therefore, there is no ambiguity in which path will I take for a particular string, there is exactly one path, which means that for every state on every input symbol, there is exactly one transition. For every state on every input symbol, there is exactly one transition, but though some books define it as for every state on every input symbol, there could be at most one transition. For example, you might actually define a transition or not define a transition. What is important here is there should not be multiple transitions. For example, here in the same example where we had from state 1, there is no transition on digit. So, this is a deterministic finite automata only. Okay. And from 2, you have transitions on letter as well as on digit. Okay. So, this corresponds to an at most one transition example. So, this is what we say, and so deterministic finite automata is going to be faster in string matching, because for every string there exactly exists one particular path from the start to the final state. Now, an alternate in a DFA, no state has an epsilon transition. This is going to be another input, that is, without consuming an input symbol you cannot change state. For each state S and input symbol A, there is at most one edge labeled A leaving S. To describe a finite automata, we use a transition graph or the transition table. Now, whatever we represented as a delta, the delta could be represented either as a automata which we saw as a graph, or it could be as a simple table which is going to be a mapping from Q cross sigma to Q. This is what we say recognition of tokens. We just now saw the example, letter followed by letter or digit the whole star. So, construct a DFAM which can accept the strings which begin with the A or B or begin with a C and contain at most one A. So, this is one example I am going to talk about here, where other than the example of defining variables in C, we can have an example which says which begins with a A or a B or begin with a C and contain at most one A. So, how do you interpret this? Begin with a A or a B, or if it begins with a C, contain at most one A. Okay. So, this is the example which we have. So, let us say you are going to have a start state. There should be definitely a start state and there should be exactly only one start state. And so, this is one path, that is it can have either a A or a B. So, this is one path where you have two states. The strings are A comma B. So, that is what I have shown here. You can have either a string A or it could be a B. Okay. And if it contains a C, okay, if it begins with or a C and then it can contain at most one A. Okay. So, from C you can have at most one A. You can have a C and then followed by that I can basically have one A. Okay. So, this is one path, it can contain a A or a B, and then other one is if it starts with a C, it can have at most only one A, which is shown here, and then one A. Okay. So, this is the alternate path. If it starts with a C, I will have only one A, but I could have any number of B's and C's. So, first string will be CA or CCA or CBA or CAB or CABC, etc. So, this is an alternate path. So, I have two different paths. One is it can begin with a A or a B and then it can contain any other string. Other one is it can if it starts with the C, then it should have only at most one A. So, there is an AND condition here if it is available, if you could remember. So, that is what is being stressed here. Construct a DFA M which can accept the strings which begin with a A or a B or begin with a C and contain at most one A. So, what is the first string? It is a A or a B, okay. And then after, if I see a A or a B, following that I can contain any number of A's or B's or C's. And then the second one is if it begins with a C, it can have only one more A, but no more, there is no restriction on B's and C's. So, that is what we have been talking about here, where we had some this example. So, if it starts with a C, it has only one A. If it starts with a A or a B, I can have any number of A's, B's and C's. Constructing a DFA is very difficult because you are very strict on the number of edges that can leave a particular state on an input symbol. It can be either a 0 or a 1. I can have one edge or no edge for an input symbol. Therefore, what we normally do is we have a variation and a flexibility. That flexibility is what is called as a non-deterministic finite automata. Now, what is the non-determinism here? From every state on every input symbol, I can have multiple transitions. That is, from Q state 1, you can have an edge on A to 2. From state 1, you can have an edge on A to 3. From state 1, you can have an edge on A to 3. So, multiple states you can basically go. So, again it is a phi tuple consisting of Q sigma delta Q naught and F, and Q naught could belong to Q and F is a subset of Q. These two definitions are same as in the case of a DFA, but the only difference being delta is a mapping from Q cross sigma to 2 power Q, where 2 power Q is called as the subset states of the NFA. Okay. It is NFA for short, non-deterministic finite automata. Since I have multiple paths, for a particular string to belong to this particular automata, there could be multiple paths, that is from the start state to the final state on an input string you can have multiple paths available. Out of all these multiple paths, even if one path is going to take you to the final state, you will call that as a string of the automata. Okay. So, there could be multiple paths. So, therefore, string matching is going to be taking some more time rather than that, some more time compared to a deterministic automata, because a deterministic automata there is exactly one path. Here there are multiple paths available, and out of all these available paths, supposing even one path, if it takes you to the final state from the start state, you will call that string as belonging to the automata. So, what we normally do is there is one more variation which is called as non-deterministic finite automata with epsilon transition. Now, this is additional flexibility where you could define some edges as labeled as epsilon, that is without consuming input symbol you can go from one state to another state. So, the string will remain same. Again, whatever is applicable for NFA will hold good here also, but it gives you a little more flexibility in the sense that you can also take a transition on epsilon from one state to the other state. So, this is still therefore slower than NFA for string matching. So, what is the observation here is in a NFA the same character can label 2 or more transitions out of one state. In NFA, epsilon is a legal input symbol. A DFA is a special case of an NFA, because a DFA is what? It is also an automata where from every state you have exactly one transition as against multiple transitions possible. Okay. So, DFA can be thought of as a special case of an NFA. So, what we continue on the same discussion, an NFA accepts an input string x if and only if there is some path in the transition graph from the start state to the final state. A path can be represented by a sequence of state transitions called moves, and the language defined by NFA is that of input strings it accepts. So, normally how do we write this is it is defined as L is equal to set of all strings W such that delta of Q naught comma W is equal to F such that F rather I can say that it is going to be containing some union of states R such that R is a subset of F. This is for an NFA, that is set of all strings W such that you can go from the start state to the start state on this input string to a set of states, because in NFA you will go to multiple states, okay, R such that R should be a subset of F. That is going to be your condition. Now, what is the big deal? You have NFA to define patterns, you also have regular expressions to define patterns, but sometimes a DFA representation is easier. Okay. So, what we normally do is we can convert one from the other. Now, all these pattern definitions, for example, your DFA, your NFA with epsilon, regular expressions, all caters to the same class of language called as regular language. Okay. So, therefore, if I could construct a NFA, I should be in a position to construct a DFA also for the same language. Similarly, if I could construct a regular expression, I should be in a position to construct a DFA also for the same language. So, with that in mind, we can convert one representation to the other representation for pattern definition. Okay. So, we could convert one representation to the other representation for pattern definition, and that is what we are going to talk about in this module and subsequent modules. So, you normally say a regular expression could be converted to a epsilon NFA using Thompson construction algorithm, and an ENFA could be converted to a DFA using the subset construction algorithm. So, these two are possible. Once I do this, what happens is I have converted my regular expression to a DFA, because regular expression sometimes for some problems writing a regular expression is easier, but DFA is probably going to be faster for string matching. So, I could convert it to a DFA, and vice versa. I could also get a DFA and then convert it back to RE if necessary. Okay. So, we are going to talk about the first algorithm to start with, where the algorithm is a step based upon induction. So, what is the basic assumption is, for every regular expression there is going to be a corresponding NFA available, because I just now said the language accepted by a regular expression or an NFA or a DFA are going to be the same class of language called as the regular language. So, what we do is, given any input symbol, that itself could be looked upon as a string. Now, this string corresponds to a regular expression R. So, I am going to say, for example, given the smallest regular expression, which is nothing but the input symbol itself, call it as R. Now, there will exist a corresponding automata, okay, which we call this as an NFA with epsilon transition. We are going to define RE to ENFA. Okay. So, we are going to have a corresponding epsilon NFA here, which we write it as having a new start state, a final state, and there is an edge from the start state to the final state on this input symbol A. So, this is your base NFA. Now, after this, what are the possibilities? I can form regular expressions using the regular expression operators. The basic operators are OR operator, which is the union operator, AND operator, which is the concatenation operator, and the clean closure operator. Now, if I have an OR operator, OR union operator, then what I do is, this is a RE, S is an RE, T is an RE. So, I have an automata corresponding to S, I have an automata corresponding to T. Okay. I have an automata corresponding to S and I have an automata corresponding to T. Now, I will introduce two new states, one as a start state and one as a final state. Remember that these two automata has one final state each and one start state. Okay. This is my base automata. Okay. So, I will do what? I will have an edge from the new start state to these two existing start states on epsilon. I will have a transition from the existing final states to the new final state and epsilon, and then for this new automata, this is my start state and this is my final state. So, I am going to introduce two states, one is going to be the start state, other one is going to be the final state, and there is going to be an edge from the start state to the final to this existing start states on epsilon. There is going to be a transition from the existing final state to the new final state also on epsilon, and for this combined automata, this is going to be my start state and this is going to be my final state. So, this is how I construct a new automata for a regular expression involving an OR operator. The next one is going to be the AND operator. Okay. Again, I have two base regular expressions and the corresponding automata. I am going to join them together. What am I going to do is, I am going to make the final state of the first automata align with the start state of the second automata. Okay. This is one methodology. An alternate one would be, if I have something like this and this corresponding to n of s and n of t respectively, I can join these two using an epsilon move also. This is a possibility. So, rather than this, what happens in the final automata is, the first automata's start state will become the overall automata's start state, and the second automata's final state will become the overall automata's final state. So, this becomes the start state and this becomes the final state. Now, these two have been merged. So, this is one variation, an alternate variation is also this. This is also a possibility. So, this is how you will form a regular expression, you will form an automata NFA corresponding to a regular expression which is formed using by joining two operators, I mean two REs using a OR AND operator. The next one is the clean closure operator S star. So, again what happens, I have a base RE constructed and the corresponding automata here N of S. I will introduce two states, one start and one final. Okay. I have a transition from this state to this state on epsilon, this old final to new final on epsilon, new start to old start on epsilon, old final to old start on epsilon. So, this is how it is going to be modeled, new start to old start on epsilon, old final to new final on epsilon, new start to new final on epsilon, old start final to old start on epsilon. This is how I construct an automata corresponding to a RE which is formed using a clean closure operator. Now, the simple algorithm will be construct the basic NFA for each of the input symbols, prioritize the operators. Okay. The operator's priority will be parenthesis first, followed by star, followed by dot, followed by R, and use the above discussed variations and form a NFA. This NFA will be with epsilon transitions. Now, example, let us take A or B the whole star followed by A B B. So, parenthesis will take the highest precedence. So, I have to first construct A or B. To construct A or B, what will I do? I have to first construct A, construct B. Okay. A is simply having having one state and having another state and then having an edge between these two states. And then A or B, how do I construct? I add a new start state, I add a new final state, combine them with epsilon, combine these two with epsilon, and that is going to be my A or B. Now, how will A or B the whole star look like? Add a new start state, add a new final state, make a transition from here to here on epsilon, make a transition from here to here on epsilon. That is new start to new final on epsilon, old start final to old start on epsilon, new start to old start on epsilon, old final to new final on epsilon, and you have to rename your old start as new start as 0 and new final as the corresponding final state as your combined automata. Now, after A or B the whole star, I have to find out A B B, right. So, what did we do? We have an automata for A, we have an automata for B, we have this automata for B. So, what did we do? We have to just merge. How do I merge? I have to merge the final state of the first automata with the start state of the next automata. So, the 7 correspond to the final state of your first automata, and here 7 is your start state of the new automata. So, these two have been merged. Similarly, I have merged this and this, I have merged this and this. So, connecting an AND operator is pretty simple in the sense that I have to simply overlap the final state of the first automata with the start state of the second automata and so on. Okay. For example, how will this would have been looked like? I would have got a new automata something like this for the first one. This corresponds to A or B the whole star. For example, say I would have got A here. Okay. This corresponds to A. I am merging these two. Now, what is this number? This is 7. Since I am merging these two, I am calling this state itself as 7. Similarly, I would have got some automata here for the B, for this B basically. I am merging these two now, that I am calling it as 8. Similarly, I am merging these two, I am calling it as 9, and the last one is going to be called as final state 10. So, for the new automata which corresponds to A or B the whole star followed by A B B, I have a new start state called as 0 and I have the old start state, a new final state called as 10. So, after this this is my automata. Now, after this we have to convert this NFA to DFA, because we already know NFA is slow in string matching, and on top of it an ENFA is much slower than NFA. So, our ultimate aim is to convert the regular expression to a deterministic finite automata, which we are going to go through by converting it to an ENFA and then converting the ENFA to DFA. This algorithm is called as the subset construction algorithm to convert ENFA to DFA, and the first algorithm we called it as Thompson's construction algorithm to convert your regular expression to ENFA. So, the subset construction algorithm is basically will convert your NFA to DFA. Okay. So, now what you require as input is, the input will be an NFA having S state of states sigma, move, S naught and Z, and your DFA will basically have Q, sigma, delta, I naught and F, and both should accept the same language. So, this is going to be our prerequisite. So, as of now what we have done is, we have basically converted your regular expression to epsilon NFA, which requires a simple logic on the sense that you need to look at the regular expressions individually, construct it, and then using the operators determine the operators, prioritize the operators, and based on the priority value you will merge them into a single state. So, this can be used as one method of pattern matching, which is going to be called as token recognition. Okay. You are specifying tokens and that could be used for token recognition. So, specifying tokens we have seen are regular expression, and then regular expression could be converted to a epsilon NFA for specific pattern matching techniques. So, with that we are going to stop this session, and we will continue the discussion on subset construction algorithm in the following sessions. To summarize what we have discussed in this module, we have basically understood the need of representing patterns using DFA and NFA, and NFA with epsilon transitions. We have understood that DFA is faster, but constructing a DFA is going to be difficult because of the restriction it puts on the transition function. NFA construction is easier, but it is slower in string matching because there are multiple paths for a particular string from start state to the final state. So, therefore, we looked at converting every automata, be it NFA or ENFA or even a regular expression, to a DFA. So, the process will involve converting a regular expression to ENFA, and that is what we have basically understood as an algorithm in this particular module. Thank you.